Beyond the nose and mouth lies a fascinating and intricate journey of breath that extends deep within us. While the nose and mouth are the entry points for air, they are merely the gateways to a remarkable expedition within our bodies. Every day, we engage in approximately 25,000 inhalations and exhalations, and the true purpose of this rhythmic exchange lies in the inner realms of our being. As we venture farther along this path, the journey becomes increasingly surprising and strange. The air we breathe travels down the windpipe, known as the trachea, which branches into smaller passages called bronchi. These bronchi extend further into the lungs, branching into a vast network of tiny air sacs called alveoli. These minuscule structures, numbering an astonishing 500 million, are like miniature bulbs at the end of the bronchioles. They serve as the sites of gas exchange within the lungs. The magic of respiration truly happens within these delicate alveoli. The journey of breath from here onwards becomes intertwined with the circulatory system, a vast web of vessels ensuring the oxygenated blood reaches even the farthest reaches of our being. But before we discuss this any further, kindly subscribe to this channel and hit the bell icon so that you will be notified when I'll upload a new video. Okay then, let's proceed. In the alveoli, oxygen from the inhaled air diffuses into the surrounding capillaries, where it binds with red blood cells and is transported throughout the body. The oxygen-rich blood, now revitalized, courses through an intricate network of blood vessels, delivering life-sustaining oxygen to every oxygen-hungry cell in our body. Simultaneously, carbon dioxide, one of the end products of cellular metabolism, is released from the bloodstream and expelled during exhalation. Let me clear the much-touted myth that we lose weight through workouts and profuse sweating. The prevailing notion of weight loss through sweating profusely or burning off fat is not entirely accurate. The process of respiration and the role of carbon dioxide in gas exchange are well-established principles in basic biochemistry. However, the connection between carbon dioxide and weight loss has been widely overlooked. Every time we exhale, we release carbon dioxide, and this exhaled carbon dioxide actually has weight. In fact, we exhale more fat as carbon dioxide through the lungs. The lungs, it turns out, play a vital role in regulating the body's weight. When we lose 10 pounds of fat, approximately 8.5 pounds of it is eliminated through the lungs. This weight loss primarily consists of carbon dioxide with a small amount of water vapor. The remaining portion is typically expelled through sweating or urination. Another popular but wrong belief is that carbon dioxide is a waste product and needs to be expelled. Contrary to popular belief, what our bodies truly need to function is not an increased inhale of oxygen. It may seem counterintuitive, but we require an optimal level of carbon dioxide in our bodies. Carbon dioxide is not a waste product. It is a vital component in maintaining our body's balance and well-being. It is essential for proper cellular function, regulating pH levels, and facilitating numerous physiological processes. This fact has either been misunderstood or overlooked by many doctors, nutritionists, and other medical professionals. Carbon dioxide plays a vital role in facilitating the exchange of oxygen between blood and cells through a process known as the Bohr effect. Within the red blood cells, an enzyme called carbonic anhydrase facilitates the conversion of CO2 and water, H2O, into carbonic acid, H2CO3. This reaction occurs rapidly and is reversible. The carbonic acid dissociates into hydrogen ions, H+, and bicarbonate ions, HCO3. This dissociation leads to an increase in the concentration of hydrogen ions in the blood, resulting in a decrease in pH. The presence of carbon dioxide and the resulting decrease in pH creates a slightly acidic environment. The decrease in pH triggers a series of events that affect the behavior of hemoglobin, the protein responsible for carrying oxygen in the blood. Hemoglobin has 4 subunits, and each subunit contains a heme group that can bind to oxygen. In the presence of carbon dioxide and a slightly acidic environment, hemoglobin undergoes conformational changes. Conformational changes refer to alterations in the shape or structure of a molecule. Hemoglobin is composed of 4 subunits, each containing a heme group. The heme group is a complex structure that binds to oxygen molecules. When oxygen binds to the heme group, it changes the conformation of the hemoglobin molecule, making it more compact and stable. This conformation is often referred to as the relaxed, or arced state of hemoglobin. However, in the presence of CO2 and the resulting decrease in pH, the conformation of hemoglobin shifts. The exact mechanism is still not fully understood, but it is believed that the binding of CO2 and the increase in hydrogen ions, H+, disrupt the interactions within the hemoglobin molecule, leading to conformational changes. These conformational changes cause hemoglobin to transition from the relaxed state, R state, to a more tense state known as the tense, or T state. In the T state, the affinity of hemoglobin for oxygen decreases, meaning that it is more likely to release the bound oxygen molecules. This conformational change in hemoglobin is known as the Bohr effect. The Bohr effect allows hemoglobin to release oxygen more readily in tissues where there is a higher concentration of carbon dioxide and a lower pH. This is beneficial because actively metabolizing tissues produce more carbon dioxide as a byproduct and tend to have lower pH levels due to increased cellular respiration. By undergoing conformational changes in response to carbon dioxide and pH levels, hemoglobin optimizes oxygen release, ensuring oxygen is efficiently delivered to tissues. This mechanism helps maintain the balance between oxygen and carbon dioxide and supports the oxygenation of actively respiring cells. In the muscle cells, oxygen can bind with myoglobin, a protein similar to hemoglobin found in muscle tissue. Myoglobin is an oxygen reserve within the muscle cells, making oxygen readily available for cellular respiration. It may surprise you, but our lungs can absorb only about a quarter of the available oxygen during normal breathing. The majority of this oxygen is actually exhaled back out. In today's fast-paced and often stressful world, many of us have fallen into the trap of overbreathing. We have been conditioned to breathe excessively, just as we have been conditioned to consume more food than necessary. It has become a subconscious pattern deeply ingrained within us. It has been estimated that a significant portion of the modern population, up to a quarter, experiences chronic overbreathing. This means we are taking in more air than our bodies truly need, disrupting the delicate balance of oxygen and carbon dioxide in our respiratory system. The capacity of the lungs to absorb oxygen from the air we breathe is influenced by various factors, including lung health, physical fitness, and individual variations. A healthy human lung can absorb approximately 70 to 85% of the oxygen available in the inhaled air during a normal breath. It's important to note that the lungs have a substantial reserve capacity, meaning they can increase their oxygen absorption rate when needed, such as during exercise or in situations that require increased oxygen demand. Maintaining healthy carbon dioxide, CO2, levels is necessary for proper physiological functioning. Here are some general guidelines to help you maintain healthy CO2 levels. Deep diaphragmatic breathing or belly breathing can help optimize carbon dioxide levels. This technique involves breathing deeply into your diaphragm rather than shallow chest breathing. Diaphragmatic breathing allows for a slower and more controlled exhalation, which helps retain a slightly higher level of carbon dioxide in the bloodstream. Avoid hyperventilation. Hyperventilation, or rapid and shallow breathing, can lead to excessive elimination of carbon dioxide from the body. This can disrupt the balance of CO2 and oxygen levels in the blood. If you notice yourself hyperventilating due to stress or anxiety, slow down on your breathing and focus on taking deeper breaths. Maintain an adequate breathing rate. While it is important to avoid excessive breathing, it is also essential to ensure that your breathing rate is sufficient to meet your body's oxygen demands. Breathing too slowly or inadequately can result in low oxygen levels and subsequent imbalances in carbon dioxide levels. Find a comfortable and natural breathing rhythm that suits your needs. Maintain overall respiratory health. Keeping your respiratory system healthy can contribute to maintaining proper carbon dioxide levels. Avoid smoking and exposure to environmental pollutants that can damage the lungs. Engage in regular physical activity to promote lung health and optimize respiratory function. It's important to note that individual carbon dioxide levels can vary based on factors such as metabolic rate, health conditions, and altitude. One of the simplest breathing techniques to maintain oxygen-carbon dioxide balance is to train yourself to inhale for 4 counts, hold for 8 counts, and exhale for 8 counts. Try doing this consciously, especially while doing physical work or maybe when you've got nothing to do. Start right now. It will eventually become your habit. In the next episode, we will discuss the sympathetic and parasympathetic systems involved in breathing and a few more breathing techniques that will enhance your health while dispelling myths. Stay tuned. If you liked the video, kindly share it with your loved ones so that they will benefit. Thanks for watching.